when we're looking at quadratics, we can actually use something that's known as the discriminant to determine some key features of a quadratic. Now, the discriminant can be used essentially to find how many times a linear line intersects with a quadratic line, but it can also be used to determine how many times a quadratic function might cut through the x-axis, which is what this video will be more focused on. So in this video, what we're going to be doing is I'm going to be describing where the discriminant comes from, how it determines how many times something might cut the x-axis, then using 3 examples to go through how we can use the discriminant to determine how many times it might cut the x-axis. So first of all, let's start with what the discriminant actually is. The discriminant is simply a formula, and it's a formula that says that the discriminant is equal to b squared minus 4ac if you've got the quadratic in the format of ax squared plus bx plus c is equal to 0. Now, if you've done the quadratic formula, this might seem familiar to you, and it should, because it comes directly from the quadratic formula. The quadratic formula that we use to find the solutions to this is x equals negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And as you can see, what we've actually got is this b squared minus 4ac that belongs under this square root. So we can essentially rewrite this to say that x is equal to negative b plus or minus the square root of the discriminant all divided by 2a. And this triangle, this delta symbol that we use, by the way, is what we use to represent the discriminant. So now we know this, let's consider 3 different examples that our discriminant might be. What if our discriminant was a positive number? So we're saying that our discriminant was greater than 0. Well, what that will mean is we'll create this plus or minus a number of some kind. We don't necessarily know what that number is, but our solution will end up adding and subtracting a positive number. So what that will in essence create is 2 solutions. And when we're looking at our graph, if I just sketch one in here, it's essentially going to cut our x-axis twice when it's greater than 0. So it's going to have what we call 2 real roots. If our discriminant is equal to 0, well, when we use this quadratic formula, we're going to be plussing or minusing 0. So essentially, we're going to be adding the same number or subtracting the same number. We're not going to change the solutions. There will still be a solution. The solution will be negative b divided by 2a, but there's only one of them this time. So what that indicates to our quadratic, when we sketch it, is our quadratic is going to come down and just touch the x-axis just the once. There's only going to be one real root. We sometimes call this a repeated root. The third situation to consider is, what if this discriminant is less than 0? Well, when it's less than 0, we're doing the square root of a negative number. Now, we can't do the square root of a negative number without creating an imaginary number, an imaginary solution. So there's no real solution that exists here. And essentially what you create in that situation of our graph is where it never cuts the x-axis. So our quadratic is either completely above or completely below our x-axis. Now, it's important to note here that the discriminant won't tell you where it cuts the x-axis. It'll only tell you how many times it cuts the x-axis. And that can be useful when we're trying to get a picture in our mind of what this function actually looks like. But let's give now 3 examples of using this discriminant to determine whether there's 2 solutions, 1 solution, or no solutions to our quadratic. So let's start with the function y equals x squared take 2x take 3. Remembering that I'm using the discriminant here to determine how many times it cuts the x-axis, rather than using the discriminant to find how many times a linear line and a quadratic meet, which I'll look at in a future video. But for now, what we're essentially looking at right now is when y equals 0. So we're looking at this quadratic of x squared take 2x take 3 when y equals 0, because that's where our x-intercepts will be. Now, essentially, what we've got to do is identify what our a, b, and c are. Now, our a here is equal to 1, it's the coefficient of the x squared. Our b is equal to -2, the coefficient of our x, and our c is equal to -3. And we now put this in our discriminant formula of b squared minus 4ac. So b squared will be -2 squared minus 4 times 1 times our c of -3. Make that look negative. Now -2 squared will be positive 4 overall. Negative times a positive times a negative will be positive overall. 4 times 1 times 3 will be 12. So therefore our discriminant is equal to 16. From here we look at, is our discriminant less than, greater than, or equal to 0? In this case our discriminant is greater than 0. So when we're looking at this we can instantly determine that there's going to be two real solutions here. And because 16 is a perfect square, they're going to be rational solutions. So what we can essentially say here is, therefore, there are two real rational roots to this quadratic. But let's take a look at another example. What if we're looking at the function y equals x squared, take 2x plus 1? Well, the process that we use is the same. The very first thing is we need to make y equal 0. So we're looking at when x squared, take 2x plus 1 is equal to 0. Now our a here is the coefficient of our x squared, so that's 1. Our b is the coefficient of x, so that's -2. Our c is the constant, so that's 1. And now we're going to use the discriminant of b squared minus 4ac to determine how many times it cuts the x-axis. So from here, we just substitute the values in. So this will be -2 squared minus 4 times 1 times 1. -2 squared is positive 4. This will just end up being take 4. So therefore, our discriminant is equal to 0. When our discriminant is equal to 0, we know that that determines that it's only going to cut it once, or just touch it and then keep going. So what we say in this situation, to say that it's just touching and keep going, is we call this a repeated root. So we say that therefore there is one real repeated root. So what that means with our quadratic is it's just going to come down, touch the x-axis, and then keep going. But let's take a look at a third example. Let's now look at the function y equals x squared, take 2x plus 3. Once again, we're looking for when y equals 0. So when this x squared, take 2x plus 3 will equal 0. In this case, our a is still equal to 1, our b is still equal to -2, but our c is now equal to 3. And we're using the discriminant here of b squared minus 4ac, trying to determine how many times it's going to cut the x-axis. So we substitute our values in. So this will be -2 squared minus 4 times our a of 1 times our c of 3. When we do this, this will be positive 4 minus 4 times 1 is 4, 4 times 3 is 12. So our discriminant works out to be 4 take 12, which is -8. So what we can determine here is our discriminant is less than 0. Now when our discriminant is less than 0, that tells us that it never cuts the x-axis. So there's no real roots here. And that's what we say. Therefore, there are no real roots to our quadratic here. So what that means is our quadratic either completely stays above or completely stays below the x-axis without ever cutting it. Now in summary, the discriminant derives from the quadratic formula, and the discriminant itself helps us determine how many times the function here cuts the x-axis, or if used differently, it can also help us determine how many times a quadratic function intercepts with a linear function, which we'll look at in a different video. So if the discriminant is greater than 0, we'll find that our quadratic is intercepting the x-axis twice. If the discriminant ends up equaling 0, that means it's just touching the x-axis. And if the discriminant is less than 0, it means it doesn't intercept the x-axis at all. What's important to note here though is the discriminant doesn't determine where it cuts the x-axis, only how many times it cuts the x-axis.